Let me give you an example of the difference between a fixed and a mixed effect, because it allows us to then also better understand why they have a very different inferential scope. So let's start with in fact, imagine the following experiment. Imagine that I wanted to know what's the average length of hair on people's head in this classroom. So what I could do is I could pick 3 people, and then for each of the 3 people, which are represented here by these curves, I will pluck 5 hair from their head, and I'll just measure their length, or something like that. So, for example, for participant number 1, the yellow participant, here 1, 2, 3, 4, and I picked these 5 hair. This is the distribution of hair length on this participant's head, okay? But of course, I'm only picking 5 hair, so I'm sampling their distribution, and I pick this one, this one, this one, this one, and that one. And then for participant number 2, light blue participant, I sample these 5 hair. And then for the dark blue participant, I sample here, 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 and here. Okay. And then sort of I can measure, what's the average for each participant. Now, in a fixed effects analysis, essentially what I'm saying, so here the only source of variation is for each participant, what hair or where am I plucking the hair from in this distribution of length? So the idea is that if tomorrow I were to pick another sample and redo the experiment, I'm picking the exact same 3 people. And I'm just plucking 5 different hair from the head of the same 3 people. So now, for example, for yellow participant, I pick these hair. For light blue participant, I pick these. And for dark blue, I pick these right here. So notice what changed from up here to down here. Well, the only thing that changed is for each person, where did I sample the distribution of hair length? In other words, the only variability in this case is measurement error. Did I pick hair towards the center, the center of gravity, the barycenter of the distribution, or did I happen to pick some hair sort of far out on the tails? And then if I go out and do this a 3rd time, it's still the same 3 people that I'm observing. But of course, I'll be picking different hair. So the only variance across my several experiments is how well am I measuring the curves for each participant. In other words, measurement error. And of course, if you were to see there's the variance between this and this and this. And if you were to sum up and divide by number of participants and number of samples, all the variances, the group distribution would probably be pretty tight. I mean, after all, there isn't much variation, right? The only variation is where am I on each of these curves. That's not a lot. Compare that to a mixed effects analysis, which is very different. Now, a mixed effects analysis essentially says the following. Now, the idea is that I have the same 3 people, right, at time point 1, sample 1, and I sample sort of these 5 hair for each person. Now, in a mixed effects analysis, and this is what is so crucial, the idea is that tomorrow, if I were to repeat this experiment again, tomorrow I would be picking 3 very different people, because participants are a random variable. See, in the fixed effects, my participants are fixed. It's only these 3. Hence, the only variance is, do I pick, the hair from the top that are longer, or the hair at the, the base of the neck that are shorter? That's the only variance. In the mixed effects model, there is that variance, right? Which hair did I pick? Where did I pick from the distribution? But I'm also recognizing that if I do this experiment again tomorrow, there's a whole population out there. I could be picking 3 different people. And then, of course, for each of them, I'll be sampling from their distribution of hair. And then if I go out and do this again the day after, it's other 3 people that I'm picking. And then for them, also I'll be sampling from their distribution. So see, you notice how here there's 2 sources of variance. First, the mean of each participant is a random variable. It could be these 3 means here, 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 or these 3 means here, 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 or these 3 means here, here, here. Plus, there's also the fact that I'm not sampling the mean, I'm sampling 5 hair from each participant, and so I'm sampling from this distribution. So there's variability across subjects, which is the first source of variability, this between subjects variability. And then there's variability within subjects. Where am I sampling within each person's distribution? Hence, if you put these 2 together, you tend to get a much broader distribution. Indeed, generally, a mixed effects analysis is much more conservative than a fixed effects analysis, because the variance in a mixed effects analysis typically is always much more. Right? And, whereas a fixed effects analysis, the variance tends to be small because it's only the within subject variability. Now, let me point out one thing. It's not that fixed is wrong. Fixed, it's perfectly fine to do a fixed effects analysis. It's just, it's not what you usually want to do. Because see, if you do a fixed effects analysis, the scope of your inference is in these 3 people, the average hair length is some number, which could be interesting. I mean, if you're, for example, working, if it's a case report, you don't need to extrapolate to the whole population. If maybe it's a very rare disease that you're looking at, and only 5 people in the world have it, and you sample all those 5 people, that's it. There's no more variability to account for, right? That's a fixed effect, and it's perfectly fine. The problem with the fixed effects is that usually what you want to do is you want to be able to extrapolate to non-sampled population. In order to do that, you have to incorporate in the uncertainty of your analysis the fact that you're aware that you picked 20 participants for your fMRI experiment, but those participants, the mean effect in each of those participants is in of itself a random variable. Whether those 20 happen to be above or below the population mean, that's a random variable. And so you need to include that uncertainty in your yardstick, right, in the denominator of the t-test. And then if something is significant, if an effect is significant compared to measurement error plus the uncertainty from the fact that that you picked 20 subjects out of the population, then you can extrapolate and say, well, this effect here, yes, I've seen it in these 20, but because I'm accounting for the fact that I fished these 20 out of a broader population by doing a random or a mixed effects analysis, you can extrapolate to the rest of the population. That is what you usually want to do. You want to be able to say, okay, I see the effect in these 20 people. It should generalize to anybody that falls inside this population.